Good morning, everybody. I'm very happy to introduce today's tutorial speakers, Phil Richards, Frank Epavier, Rodney Berwick. This morning's tutorial has slightly different format. First, we're going to hear from them, 15 minutes each or so, and then we're going to open up the floor for open panel discussion. Okay, hope you will enjoy.
I'm giving here the outline of how we're going to do this with 3 speakers. I'm going to be looking at why the solar flux is important for the IT system, why we use solar EUV proxies instead of observations, and what are proxy-driven models and how well do they work. And then Rodney is going to be talking about what are the proxies for solar EUV, where do proxies fall short, and why do we need EUV observations. And then Frank's going to tell us about the latest observation of solar EUV and what they show us and what's the prospect for future observations. So why is solar EUV important? Well, it's pretty obvious. It's the primary energy source for the thermosphere, and it's the primary ion electron source for the ionosphere. It's very important for thermospheric densities and ion production and loss. Thermospheric winds, thermospheric winds affect it particularly in the F region, and the winds affect the ion production and loss. And the photoelectron flux is very important, especially at low altitudes. The solar UV creates the photoelectron flux, which produces most of the ionization below about 150 kilometers. So it's very important. Now, I'm going back to some old Atmosphere Explorer data, which was taken from 1977 to 1980, and just showing you how the irradiance, and these are arbitrary units, don't pay any attention to the units here, as a function of the daily 10.7 centimeter solar flux, commonly referred to as F10.7. And I'm just plotting that, and this is the 33.5 nanometer radiation, and the blue line here is just a weighted least squares fit. And it's been known for a long time that when you plot it this way with daily F10.7, you get this tailing off as you go past about 180. And it's difficult to model this just with the daily F10.7 flux. However, if you introduce the average F10.7 into the equation and you plot it that way, then even with this is just again a weighted least squares fit, it's not a linear fit, you get a straight line. Of course, you always get some outliers, so and you're not going to get a perfect representation. You're going to get scatter, but still, it's a very good fit. This type of parameterization, I think, was introduced by Hans Hinteregger, and he didn't have it this way. He had coefficients here, but I found that you didn't gain a whole lot by having different coefficients in front of those parameters. Now, if you look at the time C, 33.5 nanometer, and plot it, you get a similar situation. You get this almost linear increase and then a tailing off. This is the time C data. And then again, if you plot it with this parameter P, again you get a nice straight line, but again with quite a bit of, so you can see that at particular occasions you can get quite a bit of error. And if you compare this now with the Atmosphere Explorer that I just showed before, you can see that the variation is very similar. The absolute magnitudes are somewhat different, but the actual variation with this parameter P is really similar. So back in the 1990s, I developed the UVAC model, and it's based on the AE satellite irradiance that I showed first, and it's using this proxy as for the proxy. It's done by just doing a linear interpolation between the measurements at P equals 80 and P equals 200. It had 37 wavelength bins there are a combination of bins and strong lines. Later on, I changed this. It's the same, basically the same model, but it had flexible wavelength bins. And now I'm just going to show how that compares with the timed C measurements. The C measurements are the dashed line, and this is a solar minimum. And you can see there are quite a big differences plotted on, even these are 5 nanometer bins. There are quite big difference in some locations. Point out that this region here is the important region for creating energetic photoelectrons, electrons with energies greater than about 10 electron volts. So this is a very important region for photoelectrons, and photoelectrons are very important for creating the E region. So it's very important to get this right. The original AE measurements had problems down in this region. C, I think, still has some problems, but not nearly the problems that the atmosphere explorer radiances had. And then solar maximum, a similar situation. Actually, the differences at solar maximum are not as great. And then I talked about the photoelectron flux. This is the flux here as a function of energy, in electron volts. And this is a comparison with the fast photoelectron data as the symbols here, the dots. And you can see that for a large part of this spectrum, the C data gives you both give a very reasonable representation of the fast photoelectron data. There are some issues here, up to a factor of 2, between the C representation and the data. So, and this is in that wavelength range that with the arrow that I just pointed out. This is where this is around 10 nanometers wavelength. So just to see, I'll get that out of the way. Yikes. I developed a similar model to the UVAC model using the same proxy and C satellite irradiances, and with a linear interpolation, in this case between 70 and 200, and in this case 1 nanometer bins. And this is the results you get, and it looks pretty good on a log scale. Again, here are the photoelectrons, and but you can see there are regions that there are big discrepancies, only up to about 50%. This, though, is an extreme case. This is the Halloween period where the daily F10.7 shot up to 272, but the average around, the 81-day average around there was only 140. So this is a really extreme case. And the differences, the maximum differences are around 50%, typically less than that. But when the thing that ionospheric modelers are interested in is what's the photoionization rate? And that you have to get by folding the solar flux with the cross sections. When you do that, even though some wavelengths have large differences, you're typically talking about only about a 5% difference between the C model and the C data, even for that extreme case. For less extreme cases, the difference is even less. So from an ionospheric modeling point of view, you're not looking at a large error by using a model. So given that that's the sort of area you're looking at and the convenience of using a model, it makes some sense. Also, observations are not always available, and Frank will speak more to that. One problem we have is that observations are sometimes a moving target, and the calculation you do with the observations today may be different from what you do in a year from now. So it's always a good policy to wait till the observations settle down to a certain extent. And of course, proxy models are easier to incorporate into ionospheric models. I'm going to talk now how I'm going to be using the C data, C irradiances, and comparing with model results for the ionosphere. And this just is my ionospheric model. It's called the flip model for short. And it solves the basic equations that are necessary. It uses the neutral densities from the NRL MSIS model. This, just to orient us, this is a typical situation in the ionosphere with the different ions, O plus being the dominant ion at high altitudes, and the moleculars O2 plus and NO plus at low altitudes. N2 plus is a minor ion, but it's a very important ion because it's created in large amounts. It's just lost in large amounts also. One reason for showing this figure is I'm going to be talking about NMF2, which is the peak density, in this case about 10 to the 6th per cubic centimeter, and HMF2 is the height at which that occurs. The symbols here are the data, and the lines are a model. So you can see the model is reproducing the measured densities quite well. I'm going to be presenting some data actually from Canberra. The time period I'm looking at is 2002 to 2007, using the time C solar irradiances from the model rather than actual data. It's going to be Australian ionoson data, HMF2 and NMF2. These are 1 hour data, very, very well scaled, so they're very accurate. And here's an example. This is winter and low F10.7. It's winter 2007, and it's July. Of course, this is the southern hemisphere. And you can see from the KP there's quite a bit of activity in this time period. The F10.7 is low, but you can see that the agreement between the model and the data using the C radiance model is very, very good, both day and night. It's very comforting that to get such a good fit. And if you go to solar maximum, September 2002, here again, there's some periods of very high activity. The F10.7 is quite high. On the days of low KP, again, the model data comparison is very good. But for this very high magnetic activity, you can see that the measured density goes down substantially, whereas the model stays up high. So, but this just illustrates one of the biggest problems in modeling the F region ionosphere is the modeling the magnetic activity. This is actually, I'm switching now, this is Millstone Hill data. And it's September 2005, and this is to show the effect of flares and a flare simulation. The triangles, at 100 electron density at 104 kilometers, NMF2 is also shown the measured NMF2. I didn't show the model NMF2 because it agrees very well and it just confuses the issue. So the green line is the HUVAC, my original HUVAC, running the flip model with HUVAC. And you can see it gives very good agreement, except when you get this flare. Okay, the FISM model is based on the C irradiances, but it also has a flare model built in, and you can see the blue line here. There is it does show the flare, although this flare was a little unusual and it lasted a long time, and so it wasn't well reproduced. It's interesting that the density at 104 is approaching NMF2. So the model uncertainties then are below 180 kilometers. The solar EUV radiance is very, very important, especially the flares, as you can see from the last slide. We still have issues with soft X-rays. That was a particularly good comparison between model and measurement at 104 kilometers, but we don't usually get that good agreement. There's chemistry issues, both in the ions and in the neutrals. High latitude energy deposition can change things, and there are still some uncertainties in thermospheric densities. Above 200 kilometers, the main problem is this high latitude energy deposition, the magnetic storms, which affect the densities, they affect the winds, electric fields. Solar EV, we can deal with what we have at the moment, I think. There's still some chemistry issues. At night, you have connection to the plasmasphere, and there's this O+O collision frequency problem. And in conclusion, I think the big thing is I think the C solar irradiances are producing very good ionospheric results, and it hurts me to say, but I think we should move away from UVAC and HUVAC and either use the C data or use model based on the C data. And just the models are good for normal behavior, but when the sun misbehaves as it did during the last solar minimum and maybe in the future in the solar maximum, we really need those observations to give us the ground truth. Thank you.